Hello. So one announcement at the end of today's class, if you have your marks changed, it's not reflected in the last email that I sent yesterday. If that's the case, you have to show that answer sheet if you have it to Nikita. She will take a look at it, she will update our database, our spreadsheet, and then you will get a new email, right? So by tomorrow week, you will have another email, and that will be your record of last record that I have. Right? So make sure that it's the same. Yeah, so I have some of the answers. I will give it to Nikita as soon as she comes, and we can take it. But whatever I had, I have changed it. Another doubt about time. Okay, so your deadline is today. You deadline to get any of the doubts clarified is today. Okay, so can you go to Socrates and take this quiz? I have uploaded 3 questions as quiz on the last class. So can you please go to this Socrates quiz number 6, or whichever is there right now. I think that should be the only one, right? And this is the classroom, the same room number. And there will be 3 questions. Go through the 3 questions. Sorry? Start. Okay. Let me just do it. Okay. So now there will be two questions, right? How are you seeing it? Are you, maybe you can log out and log in again. Anyway, I lost the first question also. Can you see the question now? You don't see the question? If that helps, that's good. Otherwise, I will just pose the questions and we will do it offline. It's not? Okay, let me just show you the. Is it working? Not for the second. Okay, I think it messed it up. Okay, let me just. So this is the PDF. I don't know. I don't think you can read it. I can hardly read it. High frequencies propagate longer. Good for. Anybody saying some other answer? Right. Higher frequencies actually propagate short distance. Yes. Right. That's. Let me think if I know the answer. See, I don't know all the reasons behind it. I don't know the physics behind it. But one example of this is, see, Wi-Fi signal. Right? It's a high frequency. It gets absorbed very nicely in vegetation. Right? For example, our human body is, I think, it's 75 or 80% water. Right? Vegetation, all the vegetation that we have, all the animals, and their body also, the structure has so much of water. It will absorb the signals very nice, as compared to the lower frequencies which don't get absorbed. That's one reason. It's not the whole reason. This is biological reasons. I don't know the physical reason.
We are actually made it this way. So we are very high frequency waves that are like
Yes. So
carrier waves travel longer distances. Isn't it the case?
so lower frequency means longer wavelength, right? That goes long distance. Okay. So I gave you one biological reason. I don't know the physical reason. I have to check with Shobha, I think here.
Maybe it's because of when the energy is higher, it's just the area, the spherical area which is covering, which is more. The directly goes to r square, which is the radius 4 by r square. So it is not actually the distance we are saying, but actually the whole area which is maybe
So it covers more area.
the square around it.
Okay. That could be the reason, right? Yes. See, even from the sun, there are lots of frequencies that gets emitted, but only some frequencies actually come because we have this atmospheric layer, right, which absorbs some of the signals, right? But I'm just see, this is particularly true for the Earth. I'm not sure whether we can say the same thing when it's a vacuum, right? In that case, this energy will just keep propagating because there is nobody who's going to absorb. High frequency, low frequency probably will not matter. But when we talk about Earth, which has the vegetation, which has its own atmosphere, it has lots of gases, right, which absorb something. I think in that context, this is true. Okay, maybe not true for vacuum. Okay, second question, getting multiple copies of data via multipath enhances the signal, true or false? Question is, getting multiple copies of data via multipath enhances the signal. Anybody is true? Everybody is false. Why false? Right. So when you get, see, getting multiple copies is good in some context, but when we are talking about multiple copies because of multipath, what happens is they interfere with each other, right? So even if you get too much echo in a room, it's very hard to hear. That is the problem, right? If the echo is well separated in time, then it's better because you get the same signal again and again. Right? So that is the case. How is bandwidth proportional to symbol duration? Every bit that we send is a symbol and it has a duration. How is bandwidth proportional? Is it directly proportional, inversely proportional, or is it not proportional? So as the symbol duration increases, what happens to the bandwidth? Decreases? Why does it decrease? So you are saying it's inversely proportional. Can you elaborate?
Because the time taken for one symbol to go through as it increases, so the number of symbols which could be sent in that one interval be less.
Right.
The bandwidth.
Right. So as the symbol, see, if you want to send more data, what should be the symbol duration? In the same amount of time, you want to push more data.
So
Symbol duration has to be smaller. And in other words, for sending more data, what do you need? Bandwidth lower or more? Right? So as the symbol duration increases, the bandwidth it increases. So it's inversely proportional. You can look at in that term. You also is correct, but this is another way of look at it. Okay, so Okay. So let's start. The last time we looked at physical layer, and in particular we looked at the frequencies, electromagnetic radiations, and how it propagates. What is the relationship between the frequency at which we are operating, and then what are the different challenges that you face when you transmit energy over wires. Right? So these are the challenges that we saw. Then we looked at what is the relation between uh, the bandwidth and the channel duration. We looked at it in the time domain and in the frequency domain. Right? So today what we will do is we will go a little bit deeper inside the modulation technique, and at the end of this lecture we will know why 802.11 Wi-Fi and most of the other protocols which are similar to Wi-Fi use a particular modulation technique. What is the advantage of, or what is the reason in fact? Right? Without that modulation technique, Wi-Fi will not be successful. Right? So it's not something where we have lots of choices and we select one. There is a very good reason why we select particular modulation technique. So I will keep it as much as possible away from the frequency domain or time domain analysis. Also, I will try to keep it separate from the ECE point of view. Right? I will give a CSE turn, a spin to this voltage. So overall, when we look at, you all know what modulation is. I gave you a very simple example of amplitude modulation. So in amplitude modulation, we saw, depending upon whether you want to send 0 or 1, right, you change amplitude, you modulate the amplitude. But that's not the only way. If you look at the carrier wave as this equation, right, it's the cosine wave, and you see which are the factors there, which are the parameters, tunable parameters there in that equation. You can change the amplitude, you can change the frequency, and you can change the phase. Right? So these are variables. Amplitude, frequency, and phase. Right? 2 pi is the constant. Time is as you progress, right? So you don't have any control over that. So these three things you can change, and because of that, the carrier wave will get modulated and show some other behavior. So what happens if we use frequency modulation? Can you think of now, using this equation, how would you encode 0 and 1? Or how would you modulate a carrier wave with 0 and 1 if you have control on the frequency? Let's you select one frequency, F1 for 0 and F2 something else, right? And then at the receiving end, depending upon what frequency you are getting, you say it's 0 or 1. How about phase? What is phase? What does phase signify? In sine or cosine wave. Do you know phase? So this is my wave. What happens if I change phase to this wave? Right? So you either shift it here or you shift it there. Right? Positive or negative phase shift. Right? So there is a phase shift, and the signal could be like this, or it could be, you start a little later and it will end later. Right? Amplitude and frequency is the same. Right? So this will be frequency modulation and this will be phase modulation. So we have three different ways: amplitude modulation, frequency modulation, and phase modulation. Right? So this is another way of looking at it. Just looking at an equation and thinking about it makes it really complex. So rather than doing that, we can put it in a constellation diagram like this. And we say this is, right? You can say this as voltage, and 0 voltage or plus voltage. And you can say this is my bit 0, bit 1. Right? These are different ways of modulation in amplitude. Right? If you consider this to be your voltage. Right? And same thing you can do even for frequency. Right? So you use two different frequencies to transmit bit 0 and 1. It's binary FSK. Right? If you do frequency shifting, we call it FSK. And you can do it for not only 0 and 1, but for other bits also, for other, right, combination of bits. Right? So you see this example now. At 1, you have certain frequency. At 0, the frequency is increased. Right? You get lots of waves. And then again for 1, it is different. Right? So you see these waves with changing frequency. So this is not, by the way, widely used in radio transmission because it consumes more bandwidth. Now, why does it consume more bandwidth? You know from lecture before the relation between the bit symbol or the duration of bit symbol and the bandwidth. Right? What happens as compared to the amplitude modulation? Why does it consume more bandwidth? If you change the frequency and you have two different frequencies, right, that itself, while in the time frequency domain analysis, you see you need more bandwidth, right, in terms of frequency. The band that you require for frequency at least has two different frequencies, right? This is for a simple case. If you have more combination of bits, the frequencies will increase. And basically, you will go to the government and say, okay, I need frequency 1, 2, 3, 4, 5, 6, 7, 8, all the way to the 10 or whatever, 16. Right? And that means you are asking for more bandwidth, which is a scarce resource, right? Which it's not really possible. So that's why this technique is not popular. Right? But by the way, this is also a valid technique. And then the other one is, as I said, the phase shift. So you use different phases of the same wave to signify different bits. So binary version of this will be phase 0 and phase pi. Shift it by pi so that there is a sufficient separation. So otherwise, if the phase shift is very small, you might get confused at the receiver. Right? But the frequency, the phase shift is significant like pi. Right? Then when you say bit 0 and 1, it looks like 2 ASC also. Why would it look like this one? So if I have a shift in phase of pi, it looks like amplitude modulation. Right. Inverts the whole wave, right? Because of that, you cannot differentiate between whether you are using amplitude or not, right? Because with the pi shift, the whole wave gets inverted, and then because of that, this is equivalent to amplitude shift gain with voltage plus 1 and minus 1. So if you have four combination, then you use 4 phases to send 2 bits. So here it's very easy and it's better also to see it in terms of constellation diagrams like this. Right? Then this thing will tell you what is the shift in the fields. Right? And if you have 4 of these, you can align it like this, right? And you get more and more. And you try to keep them as much as separate so that you don't have an error at the reception in terms of confusion between what did you send. Now, can you tell me, out of these 3 modulation techniques, which one is easy for the receiver? Right? Between amplitude, frequency, and phase, which one would be easy to detect at the receiving end? Amplitude. Why? Right. And you get it. What happens with frequency? Right. Noise. And another thing that you need is you need a lock on the signal, right? Because there is a minor variation in time there, right? And synchronize it perfectly is hard. See, in the amplitude, if you send 1 0 1 0 1 0, right? Even if they are out of sync in time, I will still get 1 0 1 0 1 0. Right? I will get it a little late, but that doesn't matter. I still get the same sequence 1 0 1 0 1 0. If I am talking in terms of phase, right, and my phase is already shifted in terms of reception, right, I am already out of sync with what transmission is happening, right? So for him it is 0, fine. For me it is already maybe I am shifted and I am considering the 90 degrees as fine. Like a pi is 0. Right? Then I'm already out of sync, and then my data will be a little different. Okay. Right? Right. So this is the different phase shift, and you see, depending on the shift, your wave will get shifted, right? And the duration is still the same. And because of that, you have multiple combinations. Right, so this is a technique which is QAM, which uses both amplitude and phase to send information. It's not like one is separate and the other one is separate. You can actually use combination of these two to send more, to send or to encode more number of bits, and you modulate the carrier wave accordingly. Now let's come to the challenge before we go there. So far, all the things that I mentioned to you is using one carrier. And it uses one carrier signal, it modulates that, and the reception also looks at the same carrier and it retrieves back the signal. Right? So these are all examples of single carrier modulation scheme. What if I have multiple carriers? Right? If I already have few more number of carriers, then I can in parallel modulate all these carriers together and send data. What is the advantage of this? What is an obvious advantage of this? If I have multiple carriers, I modulate all the carriers together and send the data. You increase the bandwidth, right? Or you send more data, the throughput increases, right? So we saw how much the relation, we saw the relation between sampling rate of hardware and the bandwidth. But if I have multiple carriers, then I can send more data. My bandwidth increases. Right? But now what's the challenge? The challenge is if I'm using multiple carriers, so these are my frequencies, F1, F2, right, at the same time. So there will be interference between these two also, because these signals are going to bounce on each other, on the material. Right? You already have problem when there is only one frequency being used, and that gets multipath effect and it interferes with itself. Right? With multiple frequencies, right, you can see the effect actually will get complicated, because there will be some overlap or residual energy of F1 on F2, and then this signal. So now the challenge is, if I have multiple frequencies, I want to utilize it to increase my bandwidth, but then I don't want any interference between it. Right? So that's what the challenge is. So can you think what could be the thing that could let us use this one? This idea. Can you think of an assumption that we can make so that we can transmit with multiple carriers but without the problem of interference? If you take 2 minutes, think, you can talk to your neighbor and think of some assumption that you will make where you don't have that interference and still you can, and then you can utilize this multiple carriers. There is a hint also on this slide. So I have put up the slides purposely. There is a hint there on the slide if you want. Okay, any guess? Anybody has an idea, clue, what could be the assumption that you should make? Will in that case we can send multiple carriers at the same time, but there will not be much of an interference. It doesn't have to be correct, because that will come a little later. But what do you think is the important point in this? In this slide, there is one point. There is one relation. Yes, very good. Right, so this is saying something. If symbol duration is less than the delay split, copies of previous symbol will interfere with the current symbol. That inter-symbol interference. What it is saying is that the duration of one symbol is less than the delay rate, the whole delay of multipath. Right? If it is this thing is less, then the previous symbol will interfere with your current. So that means if your delay is too much in multipath, right, or in frequencies, right, if it is too much, then they will bounce back and then come back again, and they will interfere with the current one. The previous will interfere with what you're saying current, right, and that is more dangerous as compared to the case where, right, there is what I'm saying is actually getting kind of amplified. With the minor shift in that delay or in the time symbol space, and what I say gets in the way amplified. Right. So this is not very intuitive. Right? So that's why I'm trying to give an analogy. Analogy may not be correct fully. Right? But mathematically, if you look at it, we'll come back to the equation and I will explain why it's happening. Right? But the thing is, if I say right now something and it bounces and comes back with what I'm saying something new, then that's a destructive interference. As compared to the case of what I'm saying right now, right? It's getting repeated almost instantaneously at that instant, right? Is it okay? Let me draw again. And if I'm sending A, B, and C and D like this, right? And if it comes like this, right? This is a more destructive interference. Again, this is an analogy. Don't take it as it is, but in a way, this is more destructive as compared to this one, right? Because you are killing your own signal, which will happen next time. Right? So that's the thing. So to come back to this, if the symbol duration is less than the previous rate, right? That means you have too much of delay. Then because of too much delay, your signal starts interfering in a big manner. And that's what we say inter-symbol interference. Now if you look at the same thing, if I'm using multiple carriers, if this is F1 and this is F2, right? And if the delay spread is such that, right, it is not going to cause big interference there. We should come back to this diagram in the next slide, like here. And it's not a problem. Right? But then when the separation is such that they start destructing each other, then it's a problem. So we will look at the frequency domain little later, but for now just think about it in terms of this delay spread and symbol duration.
So is it like that after one, if a path has been, if there has been some detection from another path, so it is the same data which is being sent to the receiver. Like for example, if A is better than B and A.
Right. Yeah. So let me give another example, which is there in the slide. If I'm inside this room, right, and if I'm using Wi-Fi, the quality will be better because, right, when it bounces on the walls, right, it almost immediately comes there, right? So you are actually locked onto the A. You get A, and you see again A, again A, again A in that very small duration. You basically get more confidence. Right? It's not destructive as compared to the case when you get B, and then you get something which is A, which is you can't ignore. There is enough power in that A also, right? And then the reception will be confused. Whether the B and A, what is it? Whether it's a B or it's an old A or it's a new A and so on. Right? So that's why wireless communication in the outside is a big problem, because there we have big buildings and you are traveling. When you are traveling on, let's say, in a car, and because of that, the signal bounces and it has long delay. And because of that long delay, you start interfering with your own transmission, right? And it gets disrupted. As compared to if you are going into a very smaller and smaller room, right? If you are put in a very small chamber, but your signal bounces, it's not going to cause big effect. You can still recover it because your first symbol and whatever you get immediately, it's within that small time duration. But that's still time domain analysis. I will come to the frequency domain analysis. Is this point clear? Any doubts about this? We can get clarified now. Right. Frequency domain, let it be for now. It's not confused. I will come to the frequency domain. And if I put both at the same time, probably it's confusing. Okay, so the idea is if the delay rate is sufficiently long, it's a problem for the receiver. Right? That's in simple words. Okay, now we'll come to the frequency and so let's look at multiple carriers now. So far we had only one carrier. We either modified amplitude, phase or frequency. Now with multiple carriers, let's look at what happens. And this is my entire bit stream. I divide the entire bit stream into two bit streams. Right? This is one and this is another one. Right? So there are two bit streams. So I'm splitting my bit stream into multiple parallel streams. If I have 10 carriers, I will take the entire data and divide it into 10 different streams. Modulate each stream with a different carrier allocated in that band. Save each stream slowly. Slowly is very important. So that no ISI happens, intersymbol interference. If you send it very fast, what happens is the signal bounces and the delay is then larger than how fast you are sending. But if you yourself send it very slow, then the delay will also be, even though it is large, your symbol duration is also large. Right? So your symbol duration and the delay is equivalent. Right? There's not much of a difference. So what you do is you divide the whole data into multiple streams, use a different frequency carrier for each one of these, and you start sending data slowly. Right? You are not greedy at that time. You are already greedy having multiple carriers. Right? So to use multiple carriers, you have to give up on something. And what you give up on something is you send data slowly. And recover each stream separately at the receiver. Right? So at the receiver, you are still going to get a very jumbled thing. But that you can recover at the receiver. The question is, will the parallel streams not interfere? Right? I have multiple carriers, all of them are operating at the same time. Will not they interfere? Right? So if you look at this, right? So this is a frequency domain analysis of stream 1. This is not time domain analysis. Right? You see, this is your carrier frequency. This is your second carrier frequency. Right? So they are separated by something. Right? You are sending it at the same time. Will they or will not they interfere with each other? Right? No. So they can, obviously. Like I said before in the symbol duration, multiple people are using it, right? You spill over on another frequency if you are sending too fast, right? And that could happen. The one thing is, it is possible to do so. It is possible to avoid interference if the carriers don't interfere with each other. See, for every carrier, we are not getting greedy and sending faster than that carrier. Right? Whatever that carrier can handle with its own band around it, we are only sending that much. And that's the reason slowly is also important. If you're sending fast, that means you use more bandwidth, and that means this gets fatter. Right? And if this gets fatter, you actually land up into the space of another carrier. right? But if you avoid it by sending it slowly, right, then it will not happen. For example, if each carrier, so another way to look at it, if this is at P, all the other carriers are at 0. It's the same thing. What I'm saying is the same thing. Look at this separation. If you see this carrier is at its peak, and that is right, this carrier, the other carrier is 0, and there will be another spectrum like this, which will also be 0 here, right? And so on. Right? So this is how you will separate it out. So the other frequency will be like this here. The another one will be like here. And that one. Right? So you arrange all your frequencies such that they are not overlapping with each other at this maximum energy. Right? And with this way, you can send data at the same time using multiple carriers. You're sending it slowly so that they don't interfere with each other. Yes, so total bandwidth is increased. Now, the obvious question is, a more important question is, you have two options. Either use one frequency band or use multiple carriers in that. Either you use your whole band and send data as fast as possible. Right? With that also you will end up using a band of frequency, big band. Or you decide I will not send fast, but I will use multiple frequencies. Right? Small. Now the question is, which one is better? Right? Now that's the question we'll leave for now. Is this question understood? Let me repeat. So one way of doing it is you select one frequency and send data as fast as possible, which will also end up in utilizing a band of frequencies in frequency domain. Right? That's this band. Okay? But your carrier frequency is only one, F0. When you use one carrier frequency, your data is very fast. And because of that, in the frequency domain, you utilize the whole band. And that's one thing. Or another option is this one. You take your data, you divide it into multiple streams. Each data stream uses a separate subcarrier, F1 to Fn, right? But on every one, you send data very slowly so that they don't overlap with each other. So multiple carriers going at the same time. Finally, the whole thing is the same. Use the same amount of bandwidth. Now, which one you should choose is the question, which we will see later on. But is this okay now? I showed you one carrier modulation, and this is a different way of doing it, where you can use multiple carriers, and you can use it as long as there is no interference like this. Right? So the assumption is you send data slowly, so that your delay spread is bigger, or your delay spread is comparative to your symbol duration. In that case, this will work. So this technique is called OFDM. Have you heard this word, OFDM? You will not heard this one, but probably you will hear it a lot often, right? Because this is the standard modulation technique and used at all high-speed systems today. All wireless high-speed systems use OFDM as the standard. 802.11 uses OFDM. So now if somebody asks you what is OFDM or what is the modulation technique that Wi-Fi uses, it's the OFDM. And it's orthogonal frequency division multiples. So this is how we do it. In simple words, it sends a parallel stream of data over each subcarrier slowly. Slowly is important. Right? So that means your card is actually doing lots of things. If you now see, right, I will complicate it a little more also. Right, but your card, the Wi-Fi card in your mobile, which is this big, right, it's doing very complicated things when it turns on Wi-Fi. And that's why when you switch on Wi-Fi, it consumes a lot of power. And Wi-Fi chips takes too much power. Right, so it's sending data slowly related to the data speed, data spread. Right? So depending on the data spread, it changes slowly. So that's why your Wi-Fi is a good way of communication within this environment. Because this environment, a room environment, has certain delay rate, and your Wi-Fi will not find it. But if I take Wi-Fi and say I want to communicate across Delhi, right, from one point to another point, Wi-Fi will fail. Because the whole calculations about delay rate, right, they get messed up. That's why we don't have Wi-Fi. We have 3G and LTE and 4G and other techniques which uses different modulation. If Wi-Fi is separate, it is good for this environment. So at receiver, it is very simple. It has to only solve one equalization, right? And that's it. Even if you use multiple carriers, the beauty of this solution is at the transmitter this is complex, but at the receiving end it's very simple. You get all these signals, right? And I will show you. You can still recover it with a very simple technique. Let me show you the technique. Any guess what would be doing at the receiving end? So at the transmitter, this is what we are doing. We have so many frequencies. We modulate all these frequencies in parallel. We transmit on all these frequencies in parallel. What should be the receiver doing? What do you think the receiver should do? Think of the simple solution, the naive solution. Okay, that's right. And this is how you're supposed to do it. At the receiving end, right, you have multiple frequency logs, right? Each one for each subcarrier. Right? You receive it and you decode it. That's how we do it. Right? This is not the way we do it. What would we do? Okay, let's look at this one. Right? Receiver is really simple, actually. Right? Transmitter receive it's very complicated. You have multiple carriers who send data slowly at the same time on multiple carriers. Right? What we do is, what you said is also correct. You can do it that way. But then the easier way to do this is if you use Fourier transform. Right? That is why you learn Fourier transform. A lot of times you wonder why are you doing this in the syllabus. What happens is DFT, if you recall, takes a time domain signal and converts it into weights, into amplitudes and phase into frequency domain. Right? And inverse DFT is the operation that inverses the whole process. DFT will take you from time to frequency. Inverse DFT will take you from frequency to time. Okay? That's easy. At OFDM transmitter, for each symbol, you take the bits from each parallel stream and map it to amplitude and phase, right? Using DFT. And now take these amplitude and phase of the n subcarriers and you perform the inverse Fourier transform to get the time domain. So what I'm saying is, if you have something like this, right, in time domain, you convert it into frequency domain, right? You do the modulation, you add up all things together. In frequency domain, you add these all things together, right? And you get a very big effect Fourier transform. And you just invert it into time domain and you transmit it using one layer. Is this okay? What happens is, right, you want to do this, so let me read it again. You take bits from each parallel streams. Right? You have this big, I showed you 2 streams. Right? If you have 10 streams, you take all these elements. You map it to amplitude and phase, right, for the modulation. Now take this amplitude and phase of n subcarriers, perform inverse Fourier transform, right? And you get the whole time domain signal and you send it. And this is the algorithm that we use, fast Fourier transform. You all know this. This is efficient implementation of DFT. And asserting in the hardware implementation make this very easy to do. So what I'm saying is, you are not doing it in the time domain. You are doing it in the frequency domain, and then you just inverse it and you send it in the time domain. Doing this thing this modulation in time domain is complicated as compared to doing it in frequency domain. Right? So you convert this into a domain where it is easy to operate. And then you just add up the signals together, convert it back to the time domain, and you just send one signal out. Right? So instead of having multiple antennas sending each one of the carriers, right, and sending it in the time domain, you just do all the calculations together in frequency domain, convert it back or reverse it back to the time domain, and you just send one signal out, which is all interfered together. Is it okay?
Why did we ever stop the interferences in the first place?
No, interference doesn't, I didn't mean interference. That's the position, right? The thing that I showed you before. This thing. Right? This is not there is no interference happening. Right? They are just overlap. There is enough separation to recover the signal. Right? What I'm saying is, in the frequency domain, you do all this, right? And you just convert it back to the time domain, and you send that signal. See, if there is if this thing is overlapping here, then it's not possible. No, Fourier only gives you time to frequency domain, right? Conversion. If the signal has got noise in it or interference, it will just give you back the signal in another domain. That thing will be useless, it will be garbage. So if I take noise and do an FFT, it's not going to give you the signal. It will give me something back. Okay, so the answer is, instead of doing this in the time domain, we do it everything in the frequency domain, and in the frequency domain, once we have done all the computations, we just inverse the whole thing and send it in time domain. So that's why your Wi-Fi chip also has got a big chip which can do Fourier transform, right? So that's why Fourier transform is so important, and every engineer has to learn it, because every chip, Wi-Fi chip, has got an FFT inbuilt inside it. Right? You may not use it FFT as FFT, but every day you are using FFT. For every packet that you transmit is using FFT. Right? So that's why it becomes so important. Yes. 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 So that's the thing. So the bandwidth is still the same. So I haven't answered the question why to do it in this separate subcarriers, and why not just one carrier and send it. Right? But the bandwidth is big still. And so we utilize bandwidth in a different way. We utilize so that we use small carriers in between, and everybody is sending its own way.
This is just a representation. This representation of the same thing.
It's the same signal. There is no magic happening here.
The transmitting hardware sort of thing remains absolutely same.
It's the same. Right. So this is the processing that you do on a CPU. Right? You take the signal, right? You apply the FFT, which is the whole computation, and you know FFT computation. Right? You do the addition of these multiple carriers there, and then you do inverse FFT, which is again on the CPU. We have not touched the antenna yet. Right? And when everything is ready, we just take the antenna and send it. That will be time domain. Right. So now coming back to the question is, when would OFDM work? Right? What is the thing that makes OFDM so popular and it makes it work? So you remember that every channel has an impulse response function H. Right? When you send the data, the H will act upon the signal and you will get some other output. You will not get. Ideally, H should be identity function. Right? So what we send is what we get. Right? But in reality, it's not the case. H will act upon. So in DFT terms, it's called channel frequency response H. So this is the time impulse function and it's H, small h. In DFT world, we will say it's the frequency response capital H. So this captures attenuation of each frequency in that band. Right? Every frequency changes some bit. Now, again coming back to the delay spread, the concept of delay spread. So with large delay spread, frequency response of the channel varies with the band. See, the channel that we have, this physical world, is very complicated. Right this instant, the channel acts upon signal in some fashion. Next instant, I have moved from here to here, right? You have moved from here to, let's say, here. Everything, something has changed this environment. Even if you move a bit, right, what will happen to the Wi-Fi signal changes, right? So at every instant it is changing. And if you have a long, right, response, when your signal bounces and comes back, right? In that case, what happens is, I send the data, and by the time you receive it, the whole channel is changed. In fact, if I start sending the packet, my first bit channel does something to that, and my last bit channel does something totally different to that. And so that's the problem with Wi-Fi. And if you see, when you are on the road and all the cars going and moving, right, people moving, everything changes. By the time you send data, right, every bit gets modulated in a little different fashion because of the channel condition. Right? And that complicates the thing. It's not the same thing for the wired communication. I send one bit, wire is exactly the same. Right? That one bit, if every one bit is getting half the voltage, it will happen for all the bits. Every voltage will get half. But in the wireless channel, it changes very fast. Right? So to say, if with a large delay spread, frequency response of the channel changes, varies with time. Right? So at receiver, we need to estimate this complex H to invert the channel condition. Frequency response stays the same for the entire duration of the band, right? And that's why it is good. So if that's the case, this is the case. So channel frequency response is almost constant. It's not exactly. So this is constant, right? But you see, this is not very bad as compared to this case, where every frequency has got some different impact on the because of the channel. Right? So that means in the wireless, if your delay spread is long, right, every bit that you send will have different effect because of the channel condition, and that will complicate the thing. Right? Now, can you guess the answer for that question that I asked you? I asked you a question. Which one is better? This one is better or this one is better? The answer is right there. Is using multiple carriers better or not? Why is it better? Yes, that's correct. Why is it better? It's still same, right? What is happening here is every sub-carrier frequency band is so small, right? The channel, the environment doesn't have much scope to change here, right? But if your band is so large, right, you're using almost all the frequencies there, right? The channel condition will vary and it will impact everything in a different way, like this, right? But if your band is so small, right, the environment is not going to change it a bit different. So every band you can recover nicely, right? And with that, this is better, right? So what I'm saying is, if you send a very big amount of data in parallel, like this, right, somewhere it will get damaged. If you send small bits, right, small pipes, it will not get damaged that much. Right? If you have a very big fat pipe, somewhere along the way it will get damaged. But if you have very small pipes, environment is not going to damage those small pipes, right? Because they are so small. It's like a big tree. If you have a big tree and there is a storm, right, there is a big chance that the tree will come down. If you see all the grass, right, the thin plantation, thin stems, they can survive the storms, almost all of them. Right? It's the same analogy. You don't take the analogy as it is. Right? There could be little differences here and there, but what is in principle is this is happening. Right? If something big gets damaged, right, it gets damaged. The probability of damaging the very fine small things is very low. Right? So this is why we use, although we have a very big frequency band, right, we don't use one carrier frequency, we use multiple carrier frequencies, and we modulate separately. We send data now slowly on each one of these. And that's the compromise we do. We're sending data slowly on each one of these. But then the probability of recovering the entire data at the receiver is good. Right? Because the environment is like this. It's because of the environment, right? We are looking at the nature and we adapted the wireless. It's not the other way. And we did not come up with the technique and ask the nature to adapt. Right? Nature is there. It does something. We learn from it, and that's why we chose to do it this way. Yes.
Making all this one signal, sending it one signal. So that one signal, you send a transmitter, that frequency creates one new signal and sends that one signal. Usually 20 carrier. So then that makes it one carrier.
No. That's not. It's not going to make it one carrier. Right? It's just that you take computation in a different dimension. That's it.
But you're sending one signal.
See, here also when you send it in parallel, right, it's all still one. If I have 10 antennas, doesn't mean it's going 10 different ways, right? It's the same environment. If I'm standing here now, I'm getting all the 10 channels. It's the same. They will come together, right, anyway. I cannot separate them in this space.
The one signal will still get affected by the environment. Because that one inside just small components, but
Right.
that is still one.
Right. So that's you can say the non-intuitive part. Right? It's something that if you look at the computation, that's why I gave you an analogy. Right? But don't take the analogy as it is. Still finally what holds true is this one. If you look at this one, right, that will make it clear. Right? Every small subcarrier will get affected. So that thing of doing FFT and inverse FFT, it's just an optimization. Right? It's an optimization of what we plan to do, which is using multiple subcarriers. It is not fundamentally changing anything. Right? And that's it. If you do it without subcarriers, the whole signal is different and it is vulnerable to this thing. See, the bits that you send here and here are very different. They are not the same. Right? And because of that, like the coding, if you use coding, then you can recover some data. That is the idea there also. Depending upon which coding technique you use, then you can recover or lose data. So read the slides, right? I can go over it again if you want, right? Right. So just to now, I will try to summarize these things together, right? I have introduced lots of things in non-technical terms. So I just put technical terms to this, and then we'll close this. So a large spread of H in time domain means more variation of H. Right? If you have a large spread, right? If large spread, that means the capital H frequency domain also has lots of variation. Right? That's what I showed you. So what I'm defining now is coherence bandwidth of a channel, of any given channel. This is a channel. Right? What we are seeing here in the room is a channel. So that is the bandwidth over which the channel frequency response capital H stays the same. So what is the coherence bandwidth here? This is the coherence bandwidth. It's almost the same. So channel is not going to affect it differentially. Right? So that is the coherence bandwidth. Right? That is what we see in the environment. You give me the channel, I measure its coherence bandwidth. Right? It's not something the engineer decide. It's something that the nature has already given to us, like G, the small g value. Right? Something similar to this is this coherence bandwidth for any channel. Nature will give it to us. We just take it as it is. And coherence bandwidth is inversely proportional to that delay spread. If you have more delay spread, then the bandwidth gets lesser. So in channels with lot of multipath, coherence bandwidth can be lower than the width of the channel. Right? So what is this saying is if you have lots of multipath, then the coherence bandwidth gets smaller and smaller. And if you have too much of interference, right, the coherence bandwidth will be small. Right? You will have a constant response over only a very few frequencies. In Wi-Fi, channel bandwidth is 20 megahertz. At 2.4 gigahertz, our bandwidth is 20 megahertz. That's given. That's we decided, not the nature. And we decided it's 2.4 gigahertz and the bandwidth is 20 megahertz. Because that's what government gave us. Coherent bandwidth is sometimes lower than this one. Right? In that particular scenario, for 20 megahertz and a room-like environment, coherence bandwidth is sometimes lower than this. Right? So that means for 20 megahertz whole thing, environment will work a little differently. Right? The coherent bandwidth is smaller actually. The environment says I will have a constant response not for the whole 20 megahertz, but some part of it. Right? And because of that, right, we have to use OFDM. Right? We have to use, if we want to do Wi-Fi, we have to use OFDM, and that means we have to divide this whole 20 megahertz into different subcarriers. That's the last line. So what it means is we cannot use whole 20 megahertz like this. We have to divide it into subcarriers, and we have to use and send our data over these subcarriers so that the coherent bandwidth is almost equal to that separation between two subcarriers. That's the coherence bandwidth. This is. Okay. So this is the last slide, so let me just go through it. But I will summarize this thing. Right? So if you look bandwidth, 1 over the bandwidth is the time. So if you look at it, the time space, if coherence time is greater than the packet duration, then you can assume the channel will act equally good for all the entire duration of packet. But if your coherence time is less than the packet duration, then the channel changes even when you have finished transmitting the packet. And this is very complicated. If I start sending one TCP/IP packet, and by the time you get it, the channel condition is varying. And it's good, bad, good, bad, good, bad, right? And every bit gets affected differently. So for the receiver, it's hard now to decode this channel. Right? So the packet, right? And ideally, what we want is this one. We want coherence time to be greater than the packet duration. Right? So, which one? So this is the bandwidth which is in the frequency domain, and I'm saying the same concept in the time domain. In the time domain, right, we call it coherence time. We have defined it here. Coherence time of a channel is the duration of time for which the channel response stays the same. That means channel will act upon that whole duration exactly the same way. If it's going to damage the packet, it will damage it equally. Right? And if it's not going to damage it, it will be good. Right? Right? So that is the channel response stays the same. It's not like half the packet is good and half the packet is bad. Right? That will not happen. So if your coherence time is better than the packet duration. So if this is your packet, if this is your coherence time. Is it good or bad? And this is good because you know what will happen here. Right? It will also happen here. So the same H will happen here. Right? So you can apply the same H inverse here also and here also. Now let's look at the other condition. This is the packet and my coherence time is this much. Now what's going to happen is at this instance, this is the H. And at this instance, this is H prime. So if I want to recover the signal, I should apply H inverse here and H prime inverse here. Now you see the chip has to do more computation. It has to even change its function every time it is receiving bits. Right? So that means the decoding function itself is changing all the time, even within duration of a packet. Right? And that will take up too much battery from your mobile. Because the channel conditions are varying. The chip is trying to adapt to the varying channel condition. So it will do lots of computations for every bit. Every function is changing. right? So more the computation, more the battery, and it will drain too much battery. So that's why when you have low signal strength, like your bars are not good in your Wi-Fi, or in your laptop, right? Your battery dies very quickly. Right? If you have the full signal strength, right, and you operate on Wi-Fi, your battery will last longer. So that's why if you're getting signal and you're getting packets, doesn't mean it's good. Right? Try to get to a place where your signal strength is good, and that means this thing holds. This thing holds there, right? And then computation is also reduces. Okay, so this, what we did today. Let me go back. So initially we saw that we can do modulations in different ways. We can change amplitude, which is easy and which is better to do. We can also change frequency and phase. Right? These are also, and if you change phase in some manner, it is equivalent to changing amplitude. Right? So it's not like they are completely orthogonal. They can look similar. Then we look at a condition where we use one carrier or multiple carriers. If we have an option of using multiple carriers, whether to use multiple carriers or not. And if we saw that if the symbol duration is less than the previous bit, that is the case when it gets problematic. Right? So we should take care of this. So how do we do multiple carrier modulation? Is we take different frequencies and we divide the whole bit data into different streams, and every stream gets to a different carrier, and we modulate it and send it like this. What we make sure that we send data slowly on each carrier, so that the bandwidth required for every subcarrier, it's not big, it's small. Right? So that it does not overlap. So you see this frequency is maximum here and the other one is 0. Right? So that way we separate it out in frequency. So once we do that, we don't do modulation in time domain, because that's a complicated process. What we do is we convert whole thing. We know which are the carriers, we know what is the amplitude, we know what is the phase and everything. So we apply FFT. We convert everything to FFT. We do all these additions in FFT. And then when it's time to send data out, we do an inverse FFT and get the time domain signal, and send it. Right? That's the reason FFT and inverse FFT. And the one thing that we saw is the channel's response. Right? In frequency domain, if it is capital H, then for a small frequency, that stays constant. But as you increase the band, right, that response that channel gives to your frequencies or to your data varies. Right? So ideally what we want is this much, as constant response as possible. Right? And that's why sending using multiple carriers is better than sending just using one carrier. Right? So that's why Wi-Fi, if you look at now, since we have a bandwidth of 20 megahertz, coherence bandwidth is sometimes lower than this. Right? So even if we get the whole 20 megahertz, we cannot use one carrier and send it. We have to use OFDM, use multiple carriers and send data, then only Wi-Fi will be better. Otherwise, Wi-Fi will have lots of errors. Right? So that's the reason of using OFDM. Right? So that's the coherence bandwidth. And then in the time domain, you can call it coherence time, which is this one. If your packet size is this much, you want your response from the channel to be constant for the entire packet. It should not change in between, within the packet. Right? If that thing happens, then for every bit in the packet, you have to apply a different function, inverse function. Right? And it complicates things. And it will slow you down, it will take your battery, right? And that's why it is bad. Right? And this will typically happen outdoors. And if you are in the car, right, and you are using Wi-Fi, then it's a problem. You see, you don't get a good signal. Even if you see the access points in Wi-Fi, right, if you are in a car, you cannot really communicate very nicely. It's because of this problem. So that's how outside wireless is very complicated. Inside wireless is little simple. Now, questions, doubts on the modulation techniques and why we modulate, right? And then why OFDM? what is the channel, what is the response of the channel, right? What is coherence bandwidth, right? So then let's stop. So Nikita is not here yet. How many of you have your answer sheets you want to show? And how many of you want to take it from me and show? Or from Nikita?
So if the answer, the marks are matching as per your
Then you don't have to show. If your marks are matching with the last email that you received, right, you don't have to show. If it is not matching, then only you have to show it and get the spreadsheet updated. So let me give a call to her because she's supposed to be here. We still have 10 minutes.